Our lecture for today is series resonant converters, and we will focus on the DC to DC converters, or how we will use the resonant converter in a DC to DC conversion. Now, if you remember last time we talked about in the DC to AC converters, the series resonant inverters, right? And if you think about the DC to AC converters, from the resonance point of view, you will find that there are not many applications that can be obtained or that can be applied using the inverters, right? Because the main idea for the resonant inverters or the resonant converters in general is that we operate at a certain frequency. We operate at the resonance frequency, right? And this resonance frequency is not always there. Sometimes this frequency is 100 Hz, sometimes 1 kilohertz, sometimes it's 2 kilohertz. It depends on two factors. Number one, the components, the load resonant components, the resonant tank, which is the capacitor and the inductor, okay? Number two, the value of the frequency. Once we pick the capacitor and the inductor, okay, and fix the frequency, we'll not be able to change the value of the frequency, right? Otherwise, we have to change the value of the capacitors and the inductors. And here we have the problem. Once we obtained the values for the capacitors and the inductors, we pick the frequency. Let's say this frequency is 1 kilohertz, so the resonant inverter will not be practical anymore. Why? Because we have to fix this converter working on in this 1 kilohertz frequency, on this resonant frequency. You'll tell me, okay, what is the problem? We can just use an inverter, no problems, but the inverters usually use for 50 Hertz frequency, right? The load is 50 Hertz frequency or 60 Hertz frequency, not 1 kilohertz, not the resonant frequency. So what is the best solution then? Is why don't we use these kind of converters, the resonant converters, to work as a DC to DC, and then once we have the flexibility to operate this converter as a resonant converter, we change the voltage from DC to DC and then from DC to AC. It's up to us, right? No problems. So you'll find that the application of the resonant converters is more practical, or find there are a wide range of applications when we use a DC to DC resonant converters. So today we'll talk about the series resonant converters, DC to DC, and here you'll find that we have three parts in our converter. Part number one is the inverter part, which is the half bridge. Last time we used full bridge. Today, just for simplicity, I put half bridge. So just we have two switches. Of course, we can, if you want to increase the voltage on the output, you can use H bridge, no problems. You get double of the output voltage on the point A, B, okay? And here I replaced the two capacitors with the two power voltage sources, also just for simplicity, okay? The second part is the resonant tank. Here we have the capacitor and the inductor, and we suppose that these two components operating at resonance, okay, so their values are matching with the frequency value, okay? And finally we have the rectifier stage, which is a four diodes bridge rectifier, okay? So here we will obtain AC first, square wave, okay? Then we have the resonant tank, the capacitor and the inductor. we expect that the voltage or the current here, it will be filtered, so we will have a sine wave at the output here at CD, and then the rectified output will be something like this. Then after filter, the voltage or the current will be something like this. Okay. Before going to the mode of operations for this converter, let's recall something. We said if we have a square wave, so the first harmonic of this square wave, it has amplitude. This amplitude is equal to how much? 4V maximum over pi. Okay, let's say this is V maximum or VDC. So this is 4VDC over pi. If the maximum of the square wave is a VDC voltage, then the maximum of the sine wave, the fundamental frequency harmonic, is equal to how much? 4 VDC over pi. Also, we need to remember if we have a rectified voltage like this or a rectified current, so this is maximum, I maximum, from the voltage rectifier, from the bridge rectifier, the full wave rectifier, the rectified voltage is equal to how much? The average, 2I maximum over pi, or 2V maximum over pi. Just memorize these two things here, because we will use them when we derive the equations for this converter. Now, let's jump to the mode of operations for this converter. Now, it's clear that the output of this inverter is a square wave AC. Okay. So we expect that the voltage can be either plus VDC over 2 or minus VDC over 2, and the current also can be either positive or negative, right? So here, let's have a look at this. The input is a square wave, so we remove our inverter and replace it with a VAB power source, voltage source, from plus VDC over 2 to minus VDC over 2, right? And here the output is connected to a capacitor, so I'll say that the output here it's a V out, which is the same output on the resistor. This is CD, right? And this is AB. And here we have the resonance components, LR and CR. The current that is flowing within the circuit, within the components, within the resonant components, is equal to I out, and I'll say when it's positive, it's moving in this direction. Okay. Now let's go for mode number 1 and see what options we have. So for mode number 1, the current is positive, so the current is moving in this direction. Okay, I out is positive. Okay, and the voltage is also positive, which is equal to VDC over 2. Okay, and in this case, we know that switch 1 is on. Okay, switch 1 is on, and on the other side, for the rectification circuit side, because the current is positive, okay, and the output voltage is positive, okay, so diode 1 and diode 2 are on or conducting. Okay, so diode R1 is on or conducting, and diode R2 is on or conducting. VAB is equal to VDC over 2, and VCD is equal to plus V output. Okay, so this is for mode number 1. Now for mode number 2, here we will assume that the current is also positive, but the voltage is negative. V input is negative, minus VDC over 2, and the output voltage is also positive. Now, because if the output voltage is positive, then diode R1, diode R2 is on, okay? But on the input side, because the input is negative, okay, so the conduction will be through diode number 2, right? So not switch 2, diode 2. So here, we'll say that diode 2 is on, okay? And on the rectifier side, diode R1 and diode R2 are on, okay, or conducting. When I say on, means conducting. The current I out is positive, same direction. VAB is negative, okay, and the output voltage is positive. So this is mode number 2. Okay, now this mode, just to make our life easier, we divide these to 4 modes. If you understand well how the inverter working and how the current and voltage, when this is on, when this is off, that's fine. No need to recall all these mode of operations. Okay, but some people are still struggling to memorize or to know exactly what's happening within the inverter, within the rectifier circuit. So this will make their life easier. Okay, let's go for the mode number 3. We assume that the current is negative. Okay, so this is the other option we have. Switch 2 is on. Then switch 2 is on, current is negative, input also negative, right? And this is minus VDC over 2. The output is negative as well, so this is the other option. So at this moment, what, diode 3 and diode 4 are conducting. Now what else we have? When the input is positive, output negative, and the current is negative. So this is mode number 4. So the output is negative, the input is positive, but the current is negative. And then at this case, the diode 1 is conducting, but because the output is negative, then diode R3 and diode R4 are conducting on the rectifier side. Okay, this is plus VDC over 2, and this is mode 4. So these are the options that we have for the voltage and the current on the input and the output. Let's see how we can apply these modes within one circuit, let's say. Okay, so let's go for one circuit, which is this one, and draw the waveforms, the voltage and the current waveforms. Now again, here we have the input voltage VAB, the output voltage V out, and this is VCD. Okay, and this is before the rectification, which is a square wave, should be right. VAB is a square wave, we agreed on that. Now of course, when the current is in phase with the voltage, then we operate at resonant frequency. Now let's say that the switching frequency is greater than the resonant frequency. Okay, so we have inductive load, inductive, so the current is delayed. Now VAB is a square wave. I will say that the output VCD is a square wave as well. Here is the output VCD, and this is the current I out. Okay, we said the current is looks like this as a sine wave, and the VCD is just a square wave. Now if we want to study switch number 1, you'll find that when the switch is conducting, when the switch is on, this is a half wave, right? This is not H bridge, only one leg. So this is switch 1 is on here, and here switch 2 is on. Okay, and the voltage here VDC over 2, and here how much? Minus VDC over 2. Now when the switch 1 is on, so the voltage on this switch is equal to 0 because it's conducting. When the switch is off, so the voltage is VDC. Now let's find the current in this case. If you look at this voltage, when the switch is conducting, there is some current flowing within the transistor, and this current is equal to this portion. Okay, because at this point you'll find that switch 1 is on, So this is the current that's flowing through switch 1. Now in here the current is negative, right? The current is negative. The switch is conducting, switch 1 is on, but the current is negative, not positive. So the current will not flow through switch 1. It will be through diode 2, right? Here the same thing. The current will be this portion. When the switch becomes off here, at this point, here we have hard switching. Okay, hard switching. But here we have soft switching. Right? Because the switch, when the switch turns on, soft switching, but when the switch turns off, hard switching. Okay? Now let's go and try to find the equivalent resistance for this circuit. We agreed that this is a DC to DC converter, and the output is a bridge rectifier plus a resistive load on the output. Okay, now we can replace all circuit on the output, all the bridge rectifier circuit on the output, and replace it with an equivalent resistance according to the voltage and the current that are flowing within this circuit. Okay, so we can make AC analysis. Okay, AC analysis for this converter, or for the rectifier side. We calculate the output voltage, the output current. We just find the first harmonic for the output voltage and the output current, and then we can find, once we obtained the value, the average values for these first harmonics, we can easily find what we call the equivalent resistance. We can remove the whole part, the whole rectifier part, and replace it with an equivalent resistance. Okay, let's see how can we calculate this. If we try to find the voltage VCD, the first harmonic on the output, you will find that this voltage is equal to how much? 4 V out over pi. Okay, this is the output voltage on this is the output voltage, the first harmonic. Why? Because we said that the output voltage is equal to how much? Plus V out minus V out, right? And the first harmonic is equal to how much? 4 V out over pi. So from this we can obtain the value for this output voltage. So this is number one. Now let's look at the current IR, which is I load. The rectified current is equal to how much? 2 I out 1 over pi. Okay, rectifier current 2 I out 1 over pi. Now by definition the equivalent resistance is equal to how much? We can say that VCD 1 over the output current IO1, right? This is already obtained, which is 4 V out over pi, and the output current is equal to how much? From this equation, pi times the load current over 2, right? This pi will go down to be pi square, and this 2 will go up to be 8. So here the equivalent resistance is equal to how much? 8 over pi squared times V out over IL, the load current, the output voltage over the load current. Now what is the output voltage over the load current is equal to how much? This is the resistive R, the resistive load. Okay, the resistor on the output R is equal to how much? V out over IL, right? So we can say that the equivalent resistance is equal to how much? 8 over pi squared times R. So we can replace the whole part with this equivalent resistance. Now once we replaced the whole part, we can deal with this converter as a normal AC circuit like this, right? or as an inverter, similar to the resonant inverter. Okay, so life will be much easier if we use this equivalent resistance, right? Now let's go back and try to recall the relation between the input voltage and the output voltage. We said that VAB, the first harmonic, is equal to how much? 4 VDC over 2 over pi, okay, which is how much? 2 VDC over pi, okay? Because we said 4 the DC voltage, which is VDC over 2 in this case, over pi, okay, the relation between sine wave and the square wave. VCD 1 over VAB1 is equal to how much? In this case, the output voltage over the input voltage. VCD1 is equal to 2V out over VN, and this is from last lecture is equal to how much? We can replace the this will be R equivalent over, instead of R we have R equivalent squared plus omega LR minus 1 over omega CR squared, okay, and this is equal to how much? 1 over the root square of 1 plus Q squared omega over omega naught, omega S over omega naught, minus omega naught over omega S, okay, and this is squared, okay. Finally, we can say that V out over Vn is equal to how much? 1 over 2, because we have just half bridge inverter, and this is 1 plus Q squared omega over omega naught minus omega naught over omega S squared. And here we obtained exactly similar to what we obtained last time for their series resonant inverters, okay. The only exception is that the output voltage is half of the input voltage because we used half bridge inverter. Now, if we try to draw the voltage V out over Vn with respect to frequency, you'll find that the maximum value for V out over Vn, in this case, how much? 1 over 2. This is the maximum value, right? And again, the expectation is similar to the series resonant inverter, okay? Here we have small Q factor, okay? And then here we have large Q factor, okay? And then there are few values in between them. And here, of course, the resonant frequency, omega naught. Okay, so at this point, we finish what we call the series resonant converters. By the way, why we call it series resonant converters? Because the whole rectifier circuit is in series with the resonant network, okay? With the capacitor and the inductor. They are all in series, right? So the capacitor inductor LR, CR, all in series with the rectifier circuit. So I'll see you in the next lecture.